This training will present an overview of the new 802.11ax standard, which is the 6th generation of Wi-Fi and rebranded by the Wi-Fi Alliance as Wi-Fi 6. 802.11ax is the new 802.11 standard that will bring Wi-Fi improvements into all aspects of Wi-Fi deployments, including enterprise, small business, and commercial Wi-Fi wireless LANs. We'll start out with a very high-level overview of the building blocks of 802.11ax, then drill down deeper into each building block. This will include the discussion on OFDMA, OFDM versus OFDMA, OFDMA versus multi-user MIMO, long-distance OFDM symbols, 1024 QAM, BSS coloring, preamble puncturing, target wait times, legacy device benefits to 802.11ax, Wi-Fi 6 wave releases, and finally use cases. Before discussing 802.11ax, let's briefly take a little trip through the evolution of Wi-Fi. 802.11 has evolved over the past 20 plus years. People have been working on this since early 1990s. The first standard was published in 1997, and 20 years later, 802.11ax has now been ratified. The Wi-Fi standard started with 2.4 GHz and now supports both 2.4 and 5 GHz. The standard before 802.11ax, known as 802.11ac, only supported 5 GHz because the thinking was to encourage people to move to 5 GHz because it was so much cleaner frequency. With 802.11ax, also known commonly as Wi-Fi 6, supports both 2.4 and 5 GHz, and in addition, a new 6 GHz band as well. One big factor in this expansion of 6 GHz was the proliferation of 2.4 GHz IoT devices and the increased congestion on the existing spectrum. For channelization, the standard started with 20 MHz and was expanded to 40 MHz in 11N, and up to 160 MHz in AC as well as AX. Today, we see very little 160 MHz applications, but with 6 GHz, this might become reality. The peak PHY rate started with 2 megabits per second, and with 802.11ax, we're talking about up to 10 gigabits for wireless medium. People talk about high throughput, but what really matters is how we utilize the spectrum. High throughput sells products because it is easy for everyone to understand, but what really matters is how well the standard uses the available spectrum. This is measured by link spectral efficiency. The first standard could push 1 megabits per hertz. Today, with 11ax, we're pushing 62 megabits per hertz. The standard is becoming more efficient by utilizing the available spectrum. This is what 802.11ax was created to accomplish. As a result, you can see that 802.11ax standard was named high efficiency rather than the older standards which concentrated on throughput, with names such as 11N with high throughput, 11AC named very high throughput. Another metric was the maximum number of single user streams. The legacy standards had one transmit chain and one receive chain that allowed us to transmit one stream of data. Then 11N came along with 4 radio chains. Then we could transmit 4 parallel streams to the same device, which improved throughput and efficiency. 11AC along with 11ax, allowing as many as 8 streams. However, many mobile devices utilize 2 of those streams due to their power and limitations. So the multi-user, multi-in, multi-out, or multi-user MIMO concept came along, with the idea that if an AP can transmit 8 streams, why limit it to transmitting all 8 streams to one device? Why not multiple devices? As a result, we can break those 8 streams into 4 groups or 2 streams and send them to multiple 2-stream devices, such as smartphone with a 2-stream capability. That's essentially the multi-user concept. 11AC allows the AP to talk to 4 devices at the same time. With 11AC, we're able to do multi-user MIMO, but it is limited to only the download direction. With 802.11ax, you can do multi-user MIMO in both upload and download direction. 802.11ax introduced a new modulation scheme called Orthogonal Frequency Division Multiple Access, or OFDMA. This is new to Wi-Fi, but has been in use in other standards, especially LTE, where it has been in use and works very well. The concepts that have been proven effective and scalable in LTE are now being integrated into Wi-Fi. 802.11ax also added a modulation scheme of 1024 QAM, which allows us to do higher data rates. The maximum number of OFDM tones has increased from 64 in legacy devices up to 2048 on a 160 MHz channel in 11ax. The 802.11ax also reduced the subcarrier spacing by 4 times, from 312.5 kHz used in the past to 78.125 kHz. The narrower subcarrier spacing allows more data subcarriers, providing efficiency gains allowing 10 bits per symbol using 1024 QAM, compared to the 8 bits using 256 QAM in 802.11ac. We'll discuss many of these features in much more detail through this training, but as you can see, Wi-Fi has evolved tremendously over the past 20+ years. In the past, wireless LANs focused on theoretical peak speeds. With 802.11ax, even though the speed has increased over the 802.11ac standard, the emphasis is on overall network capacity and efficiency and not just speed. The 802.11ax is the next evolution of the IEEE 802.11 Wi-Fi standard and is effective in very dense environments, such as urban apartment complexes, also known as multiple dwelling units, college campuses, concert venues, or sports stadiums where many clients will access the internet over Wi-Fi. For 802.11n, the maximum theoretical speed was 150 megabits per stream. 11ac increased this to a theoretical speed of 866 megabits per stream, which is over a 6-fold increase. 802.11ax will increase the speed to 1,201 megabits per second, which is faster, but not the 6-fold increase like 11n to 11ac. Although the nominal data rate is just 37% higher than 11ac, the new amendment can potentially achieve a 4 times increase to the average user's throughput due to more efficient spectrum utilization and improvements for dense deployments. Performance can vary widely based on range, obstacles, other signals in the air, multipath reflections, and the quality of your access point and your client device. To address these issues, 802.11ax aims to improve efficiency in a number of ways to give you consistently higher real-world speeds than what you get with the 11ac standard. Perhaps the biggest change is a feature called Orthogonal Frequency Division Multi-Access, or OFDMA. 802.11ax uses 4G's LTE proven and foundational OFDMA technology for efficient access. This OFDMA technology allows multiple users with varying bandwidth needs to be served simultaneously. What it does is chop up each wireless channel into many smaller partial channels. This allows up to 9 different clients to talk to an AP at once over a single 20 MHz channel, 18 clients over a 40 MHz channel, 37 over an 80 MHz channel, and 74 over a 160 MHz channel instead of just one client. This improves the efficiency of the contention domain because multiple clients can use it at the same time. Through these smaller channels and the ability for multiple clients to broadcast at once, the AP has more flexibility, allowing it to allocate bandwidth to each device based on its data needs. This helps to increase overall network performance. OFDMA can work in tandem with multi-user MIMO. The gist of this is that the multi-user MIMO allows an AP to address multiple devices simultaneously instead of one at a time sequentially. Multi-user MIMO was introduced in 11AC, but only in the download mode. 802.11ax supports up to 8x8 multi-user MIMO in both downlink and uplink modes, which allows it to serve up to 8 users simultaneously for a significant capacity boost. Although part of the 802.11ac standard, multi-user MIMO has not been used that efficiently, especially in dense or diverse client transmission groups where legacy non-MIMO devices are present. That is why OFDMA and the ability of splitting the subcarriers for multiple users to access at the same time is exciting and will be more scalable. The new bandwidth being introduced in the 802.11ax standard, which we'll talk about later, might allow for multi-user MIMO to be more effective because only new devices will be using the new spectrum. Another 11ax feature is the addition of BSS coloring. This feature is called Basic Service Set Color Identifier that is attached to each PHY header to indicate what wireless LAN and device it was transmitted from. Since Wi-Fi is a half-duplex medium, only one radio can transmit on a frequency domain or channel at a given time. An 802.11 radio will defer transmissions if it hears a PHY preamble transmissions of any other 802.11 radio at the signal detect threshold of 4 decibels or greater. This is referred to as medium contention overhead. Unnecessary medium contention is referred to as overlapping basic service set, or OBSS, also commonly referred to as co-channel interference, or CCI. 802.11ax was tasked with addressing the OBSS challenge by improving spatial reuse, which is often referred to as BSS coloring. This mechanism was originally introduced in 802.11ah, known as spectralization, published in 2017, and was to address medium contention overhead due to OBSS. 802.11ax assigns a different color, a number between 0 and 63, which is added to the PHY header in the 802.11ax frame to each BSS in the environment. With BSS color, the AP can identify which frames are coming from other networks and ignore them as long as they are below a threshold of weakness to cut down the need for deferring transmission due to outside interference and avoid unnecessary slowdowns. Preamble puncturing is an optional capability feature where an 802.11ax AP adapts to nearby APs when utilizing wideband transmissions. One of the biggest hurdles with wideband transmission is that all the 20 MHz that are combined need to be clear for transmission. Prior 802.11 standards required contiguous channels for any transmissions larger than the standard 20 MHz channel width, outside of their options like dynamic channel width selection. 802.11ax provides an option to bypass channels within its transmission spectrum that are in use when it is ready to transmit. This can potentially improve spectrum utilization and overall throughput. This could be very helpful in areas where wide transmission is common that still might have adjacent transmitting legacy devices. It allows devices to negotiate when and how often they will wake up to send or receive data. TWT increases device sleep time and in turn substantially improves battery life, a feature that is particularly important to IoT devices. This allows the Wi-Fi transponder to sleep when the transmission isn't necessary, which will help preserve precious battery life. In addition to saving power on the client device side, Target wake time enables wireless access points and devices to negotiate and define specific times to access the medium. This helps optimize spectral efficiency by reducing contention and overlap between users. Although a primary goal of 802.11ax is better efficiency, more speed isn't a bad thing. Quadrature amplitude modulation, known as QAM, uses both phase and amplitude of an RF signal to represent data bits. 802.11ax supports 1024 QAM and new modulation coding schemes, or MCSs, that defines higher data rates that translates into better throughput and 25% higher capacity with 10 bits per symbol versus 8 bits per symbol with 256 QAM. More bits equals more throughput data, providing more efficient use of the spectrum. 802.11ax also introduces two modulation coding schemes, MCS10 and MCS11, which were added for the use of 1024 QAM. 1024 QAM can only be used with 242 subcarrier resource units or larger. This means that at least a full 20 MHz channel is needed for 1024 QAM. When wireless devices transmit a signal, the RF signal reaches the destination receiver directly or by reflections off the walls, ceilings, or other obstacles. This is referred to multipath. The OFDM symbol was originally designed with indoor Wi-Fi in mind. Multipath reflected RF signals are expected to reach the receiver very quickly. The OFDM symbol was composed of guard intervals followed by a data portion, then another guard interval, and then another data portion area, and so forth. The guard interval was either 0.4 or 0.8 microseconds, with this useful ODM data portion set to 3.2 microseconds. When using Wi-Fi outside, the guard interval needs to be increased to compensate for longer distance reflections. 802.11ax long OFDM allows up to 3.2 microsecond guard interval, with a data packet area being increased 4 times to a 12.8 microseconds. This gives us a much larger multipath tolerance, reduces overhead, and gives us much better throughput, making outdoor Wi-Fi more reliable and dependable. 11AC only supported 5 GHz. 802.11ax supports 2.4, 5 GHz, and the FCC has opened the 6 GHz spectrum for Wi-Fi on April 23rd of 2020. Other countries anticipate opening 6 GHz spectrum after the fourth quarter of 2020. 802.11ax will utilize a 6 GHz unlicensed frequency and was included in the standard. The 2.4 band is especially important because of the number of IoT devices on the market, which is rising rapidly. The end result of the 6 GHz process in the US is that it opened up 1200 MHz for Wi-Fi. The amount of band available for Wi-Fi in the US has remained unchanged for more than a decade. The confluence of the new 802.11ax and the new 6 GHz spectrum may just fuel a wireless industry perfect storm of disruption. Also, for the channel bandwidth in the 6 GHz band opened up, 160 MHz could become reality, and 11ax is compatible with earlier 802.11 standards. So in brief, Wi-Fi 6 or 802.11ax is designed for high-density connectivity and offers up a 4-fold capacity increase over its 11AC Wi-Fi 5 predecessor. With Wi-Fi 6, multiple APs deployed in dense device environments can collectively deliver required quality of service to more clients with more diverse usage profiles. With Wi-Fi 6, multiple APs deployed in dense device environments can collectively deliver required quality of service to more clients with more diverse usage profiles. This is made possible by a range of technologies, such as OFDMA, multi-user MIMO with 8 uplinks and 8 downlinks, target wake time, 1024 QAM, long-distance OFDM symbol, BSS coloring, and increased frequencies. These technologies will play a critical role in helping Wi-Fi evolve into a collision-free deterministic wireless technology as the IEEE looks to integrate future iterations of these mechanisms into the wireless standards to support the future of Wi-Fi and beyond.